Three, two, one.
Good day, sir. Today, I will be presenting my video presentation about distribution-based clustering. Distribution-based clustering. Till now, we have learned about the clustering methods that are based on similarity, distance, or density. This family of clustering algorithms takes a totally different metric into consideration. Distribution-based clustering is a clustering model in which we will fit the data on the probability of it belonging to the same distribution. This clustering approach assumes data is composed of distribution such as Gaussian, binomial, and etc. Gaussian mixture model or GMM clustering uses the probabilistic approach and it provides probabilities of each data point that belongs to the cluster. Here we have three clusters that are denoted by three colors: blue, green, and cyan. Let's take the data point highlighted in red. The probability of each point being a part of the blue cluster is 1, while the probability of it being a part of the green or cyan cluster is 0. Now, consider the point highlighted in the red color. The probability of point belongs to the green cluster is 0. The probabilities value of that point belong to blue and cyan colors are 0.2 and 0.8. We will see how Gaussian mixture model calculates these probabilities and assign it to the data point. A Gaussian mixture is a function that is comprised of several Gaussians, each identified by k covariance 1 to k, where k is the number of cluster of our dataset. Each Gaussian k is the mixture of comprised of the following parameters: a mean that defines its center, a covariance that defines its width. This would be equivalent to the dimension of an ellipsoid in a multivariate scenario. A mixing probability that defines how big or small the Gaussian function will be. Let us now illustrate these parameters graphically to find variance, covariance, and weights to the cluster. GMM uses the expectation maximization technique. Expectation maximization finds the value by using below two steps: the expectation step and maximization steps. The steps for each point calculate the probability that it belongs to cluster distribution or C1, C2, Ck. This is done using the below formula. This value will be high when the point is assigned to the right cluster and lower. The M step, post the E steps, we go back and update the density, mean, and the covariance values. These are updated in the following manner. The mean density is defined by the ratio of the number of points in the cluster and the total number of points. The mean and the covariance matrix are updated based on the values assigned to the distribution in proportion with the probability values for the data point. Hence, a data point that has a higher probability of being a part of what this distribution will contribute a larger portion. Based on the update, values generated from these steps will calculate the new probabilities for each data point and update the values iteratively. This process is repeated in order to maximize the log likelihood function. The distribution model of clustering are most closely related to statistics, and it's very closely related to the way in which datasets are generated and arranged using random sampling principles, and etc. To fetch data points from one form of distribution, cluster can be easily be defined as objects that are most likely to belong to the same distribution. The expectation maximization algorithm is one of the popular examples of distribution-based clustering, and it uses multivariate normal distribution. It has a major advantage over the proximity and centroid-based clustering methods in terms of flexibility, correctness, and shape of the cluster form. It is because those algorithms depends on the shape of clusters, which is adjusted by one or more hyperparameters, and if we by mistakes didn't see these hyperparameter values correctly, they may lead to unwanted results. While one disadvantage of distribution-based clustering is that we can only use it when we have information about the type of distribution of our data.